Hello, bachcho. Today we're going to look at a really clever idea from our atoms chapter, how de Broglie solved a big puzzle in Bohr's model. Now I know it sounds a bit complicated, but trust me, in the next few minutes we will make it so simple that you'll never forget it. And most importantly, everything we discuss will be 100% exam safe. Chalo, let's get started. So, we all think of Niels Bohr as a total genius. And he was. His model of the atom was a huge step forward for physics. But there was this one big mystery, a little puzzle right at the heart of his theory that even he couldn't quite figure out at the time. So what was this puzzle? Well, it was Bohr's second postulate. You know the one, it says that the angular momentum, L, of an electron is quantized. It can only be a whole number n times h bar, which is just Planck's constant h divided by 2 pi. Now here's the thing. This was basically an assumption. A totally brilliant assumption, mind you. It gave all the right answers. But Bohr couldn't explain why it had to be true. It was like he found a magic rule that worked, but he didn't know where the magic came from.
And this is the funny part. On one hand, his rule was a massive success. It finally explained why atoms don't just collapse, and it predicted the spectral lines of hydrogen perfectly. But on the other hand, there was this giant question mark. The rule felt a bit random. In physics, we really don't like random rules. We need to know the why behind everything, and that's where our next hero comes into the picture.
So then, in 1924, this young French physicist, Louis de Broglie, comes along with a truly mind-bending idea. He just asked a simple question. What if we've been looking at electrons all wrong? What if they aren't just little tiny balls? What if they also behave like waves?
And this is his famous equation. It looks simple, but it changed everything. De Broglie said that any moving particle, yes, any particle, has a wavelength associated with it. This wavelength, lambda, is simply Planck's constant, h, divided by its momentum, p. This was the masterstroke. See what he did? He connected a wave property, wavelength, to a particle property, momentum.
But hold on a second. That's the big question, isn't it? It's easy to write down a formula, but what does it actually mean? How can an electron, which we think of as this tiny point, be a wave that's going around in a circle? To help us understand this, de Broglie used a really beautiful and simple analogy.
And this brings us to the absolute core of his explanation, the idea of a standing wave. This one idea is the key that will unlock the entire mystery of Bohr's postulate.
Just imagine a guitar string for a moment. When you pluck it, it doesn't just vibrate in any random way, right? It forms these beautiful, stable patterns, maybe one big loop, or 2 loops, or 3 loops. You can't have 1.5 loops because the ends are fixed. These special, stable patterns are what we call standing waves.
Okay, now take that exact same idea and apply it to our electron in an orbit. De Broglie said that for an electron's orbit to be stable and to actually exist, its matter wave has to form a standing wave around the nucleus. This means the wave has to wrap around and meet itself perfectly. If it doesn't line up, it'll interfere with itself and just cancel out. Poof, gone. We call that destructive interference. So only those orbits where a whole number of wavelengths fit perfectly are allowed. Now, have a look at this picture. It makes it so clear. On the left, you see an allowed orbit. See how the wave fits perfectly? In this case, exactly 4 wavelengths go around the circle and join up smoothly. It's a stable, standing wave. But on the right, look at that mess. The wave doesn't fit. It's all out of sync, it interferes with itself, and it would just vanish. That orbit is forbidden. It simply cannot exist.
All right, so we have our one simple rule. A stable electron orbit must be a standing wave. Now for the amazing part. Let's use this simple physical idea and just a little bit of Class 10 math to derive Bohr's mysterious rule. No more guessing needed.
Let's do this together. It's very easy. Just watch. Step 1, our main condition. The circumference of the orbit, which is 2 pi r, must be equal to a whole number n times the wavelength, lambda. Simple. Step 2, now we substitute. We know from de Broglie that lambda is just h divided by p. So let's put that in. We get 2 pi r equals n times h by p. Step 3. Let's just rearrange the terms. We'll move the momentum p up to the left side, and we'll move the 2 pi over to the right side. What do we get? R times p equals n times h over 2 pi. And wait a minute, what is r times p? That's just angular momentum, L. So, L equals n times h over 2 pi. And there it is. That is exactly Bohr's postulate. It's not a guess anymore. It's a direct result of the electron behaving like a wave. Amazing, isn't it?
Let's just do a quick check with some real numbers to be absolutely sure. Let's take Bohr's second orbit, where n is equal to 2. The radius for that orbit is about 2.12 angstroms. So the circumference comes out to be 13.33 angstroms. Now, if you calculate the de Broglie wavelength for an electron in that orbit, you get 6.61 angstroms. Okay, final check. What is the circumference divided by the wavelength? 13.33 divided by 6.61, it's almost exactly 2. It works perfectly. 2 complete wavelengths fit into the second orbit.
Okay, pay close attention now. Let's quickly clear up 2 very common mistakes that can cost you marks in the exam. First one, so many students think an electron is either a particle or a wave. That is wrong. The correct idea is that it is both at the same time. It has properties of both, and which property you see just depends on how you measure it. This is the famous concept of wave-particle duality.
And here's another silent killer. People think the de Broglie wavelength is the actual physical size of the electron, like its diameter. Nope, that's not it at all. As far as we know, an electron is a point particle with no size. This wavelength belongs to its associated quantum wave, sometimes called a probability wave. It just tells you the scale at which the electron's wavy nature starts to become noticeable.
So de Broglie's idea was beautiful. The logic was perfect, and the math worked out to explain Bohr's rule. But in physics, a beautiful idea is not enough. We need proof. Was there any real-world experimental evidence for this wild idea?
And the answer is yes, absolutely. Just 3 years after de Broglie's proposal, 2 scientists, Davison and Germer, were doing an experiment. They fired a beam of electrons at a crystal, and they saw something incredible. The electrons diffracted, creating a pattern of bright and dark spots, just like light waves do. This was the smoking gun, the first direct proof that electrons, tiny little particles, really do behave like waves.
So, let's just summarize the most important points for your exams. Point number 1. De Broglie's big idea was that all matter has a wavelength given by lambda equals h by p. Point 2. For an electron orbit to be stable, it has to form a standing wave. Point 3. This simple standing wave condition is what mathematically leads straight to Bohr's quantization rule. And the final big picture takeaway, Bohr's rule wasn't a random guess at all. It was the first clue to a much deeper truth about our universe, the wave nature of all matter.
And I want to leave you with one final thought to ponder. Every single atom in your body, in the chair you're sitting on, in the air you are breathing, it's all held together because of these strange wave-like properties. The stability of the entire world we see depends on electrons behaving as standing waves. So, if an electron is a wave, what does that really mean about you and the solid world you experience every day? Something to think about. That's all for today.